All right, today we're pulling back the curtain on the magic that powers everything from your GPS to the internet itself. We're going to break down one of the most important algorithms ever created, Dijkstra's algorithm. It's the secret sauce for finding the shortest path.
Have you ever really stopped to think about how this works? You punch in an address and boom, in seconds your phone has the best route, weaving around traffic like it's nothing. You'd think it's some kind of impossibly complex sorcery, but the core logic? It's actually a super elegant idea that's been around since the 1950s. Let's see how it's done.
So here's our game plan for today. We'll start with the basic problem we're trying to solve, introduce the algorithm and its rules, and then we'll watch it work step by step. After that, we'll see where it's hiding in the real world and unpack the one brilliant idea that makes the whole thing possible.
At its heart, the challenge is pretty easy to describe, but way harder to actually solve. Imagine you have a network of points. Could be cities, could be computers, and they're all connected by paths. Each path has a cost, like distance or time. The big question is, how do you find the absolute cheapest route from your starting point to every single other point on the map?
And this is where the hero of our story comes in, Dijkstra's algorithm. It was dreamed up by a Dutch computer scientist named Edgar Dijkstra, and it gives us a guaranteed, methodical way to solve this exact problem.
Okay, so here's the official textbook definition. Yeah, it sounds a little dense, I know. But for now, let's just lock on to two key phrases here: greedy algorithm and non-negative weights. We're about to unpack exactly what those mean.
Let's break this down. The algorithm is called greedy because it always makes the choice that looks best right now. It always heads to the closest spot it hasn't been to yet. And once it figures out the best way to get somewhere, that's it. It locks it in, no second guessing. But here's the most important rule. It can't handle negative costs. That'd be like taking a road that makes you travel back in time, and well, that just breaks the whole system.
So let's get into the actual mechanics. A good way to think about this is to imagine an explorer. They're at base camp, and they always travel to the nearest unexplored landmark first. Once they get there, they pull out their map, update it with any new shortcuts they've found, and only then do they decide which new closest landmark to visit next. So this is the official procedure. We start by pretending every destination is infinitely far away, except for our starting point, which is zero distance from itself, obviously. Then we just repeat this loop, pick the closest unvisited spot, check out its neighbors to see if we can find a shortcut to them, update our map, and then cross that spot off our list. It's a really simple but really powerful loop.
Okay, theory is one thing, but seeing is believing. We're about to walk through a simple map and just watch the algorithm do its thing. This is usually where the logic really starts to click.
Okay, here we go. This is our starting line. We're at node 0. The distance to get here is, 0. But from this spot, every other node might as well be on the other side of the universe. We have no idea how to get to them yet, so their distance is infinity.
All right, first move. From our starting point at node 0, we can look around and see two direct neighbors. Node 1 is 10 units away, and node 4 is 5 units away.
So we immediately update our table. Their distances aren't infinite anymore. Now the algorithm has to make its very first greedy choice. Of the places we haven't been to, which one is the closest? Easy. It's node 4 with a distance of just 5. So that's where we go next. And from this new viewpoint, we look at its neighbors to see if we've discovered any new shortcuts.
And whoa, check this out. This is where the magic really happens. Look at node 1. We thought it was 10 units away, right? But it turns out, going through node 4 first gets us there in just 8. The algorithm immediately updates the path. And we've also just found our first ways to get to nodes 2 and 3.
So what's next? We just repeat the process. We look at our unvisited nodes, 1, 2, and 3, and find the closest one. That's node 3, with a distance of 7. So that's our next stop. From there, we check its neighbors and find another path to node 2.
And bam, another optimization. The path to node 2 we found earlier was 14, but the path through node 3 is only 13. So the algorithm updates its records again. It's always keeping track of the best route it's found so far.
We're almost done. Let's look at the remaining unvisited spots, 1 and 2. The minimum is node 1, with a distance of 8, so off we go. And from this final vantage point, we can see node 2, which leads to one last crucial update.
And there it is. The path to node 2 through node 1 is only 9 units long. That's the best one yet. And since all the nodes have now been visited, the algorithm stops.
This table now shows the absolute guaranteed shortest path from where we started at node 0 to every other place in the network. Pretty cool, right?
So obviously that was a tiny little example, but what's amazing is that this exact same logic is just scaled way, way up and used in countless systems we all rely on every single day.
It's not just Google Maps. When you send an email, network routers are using this kind of logic to find the most efficient path for your data to zip across the internet. Airlines use it to piece together flight itineraries, and even social networks can use it to figure out the degrees of separation between you and someone else.
Now, on a huge network like the internet, just checking every single option one by one would be way too slow. So to speed things up, computer scientists use a really clever tool called a priority queue. You can think of it like having an assistant who always has the next closest location ready for you, so you don't even have to search for it. It makes the algorithm dramatically faster and powerful enough to handle the real world.
So as we wrap this up, let's zoom back out and focus on the one single concept that really gives this algorithm all of its power.
This is it. This is the whole thing. The greedy choice. The absolute genius of Dijkstra's algorithm is the proof that by always optimistically and relentlessly exploring the closest known frontier, you are guaranteed to find the shortest path to everywhere. No backtracking, no regrets. It's simple, it's efficient, and it is incredibly powerful.
But here's a final thought to leave you with. Dijkstra's is brilliant when you have the whole map laid out in front of you. But what if you don't? What if you're a robot dropped into a maze with no idea what's around the next corner? Well, that requires a whole different kind of algorithm for a whole different kind of adventure.